also interesting that we have the choice between moving space-time or modular very faces. We have to vote in order to so enjoy Bartek's talk.
Thank you. Thank you very much for giving me an opportunity to speak here. I have to say that this talk is not really about tensor networks. I hope that you will forgive that. But maybe there is some food for thought for tensor networks-oriented people in there. So, okay, and this is work done in collaboration with these people, and its arrival on the archive is so imminent. I even put an extra digit here. The theme that probably begot this workshop, and many of us working here, our research direction started from there, or took that term, is that space-time is emergent, or we believe that it is emergent from entanglement, and holography is maybe that's just special to holography, or maybe it's just a really amazing time model of that fact, which applies more broadly. But the theme is space-time from entanglement. And we have seen what are the examples of that. We first got a hint of that in the 70s from Hawking's calculation of black hole entropy, which in the two-sided context can be viewed as a computation of entanglement entropy between the two sides. Then Tadashi's work, the Ryu-Takayanagi proposal, told us that in fact any minimal surface in ADS, or almost any, can be thought of as the entanglement entropy of some subset of a CFT. And many facts of that type have followed since then. So one thing that we can ask about is, if we believe that space-time really comes from entanglement, we should be able to explain any geometric feature of space-time using entanglement. So here is a task for all of us. What is the curvature tensor? Or how do I compute the curvature of the bulk from CFT entanglement? That's a question we may all think about. As far as I understand, no one has given an answer to this question prior to this talk and the work that we will be presenting. So potentially this is a new entry in our understanding of space-time from entanglement. I want to understand bulk curvature, but it's our the bulk connection. In fact, this object that I will describe just now, modular Berry connection, it answers more questions than that. So it answers that question, but it also answers many others in one go. So I'm very excited about that. Now, to bring everybody on the same page, let me just write down a brief dictionary of this space-time entanglement correspondence. So the first thing, which I already mentioned, is the entanglement entropy of maybe I should start with this. Let's draw anti-de Sitter space and the ADS CFT correspondence there, so we are all on the same page in terms of our drawings. So I will represent anti-de Sitter space as a cylinder. This is customary. The CFT lives on the boundary of that cylinder. So perhaps the first entry in our dictionary should be a state in the CFT. A state in the CFT is something that lives on a Cauchy slice on the boundary. So it lives on these dotted lines. The next thing is the entanglement entropy of a region A. I will just tell you about the Ryu-Takayanagi proposal now. So I will subdivide the region. I will subdivide the Cauchy slice of the CFT into two pieces. One of them will be called A. And then if I ask what is the entanglement entropy of A, what Tadashi and his collaborator told us about more than 10 years ago is that the bulk computes this, or gives it to us, in the form of a minimal surface which just subtends the region A, or which just covers the region A. The next thing that I may want to ask about is the reduced density matrix of A. So some work over the last 5 or so years more or less established that the dual of the reduced density matrix of the system A is an object called the entanglement wedge of A, which I can draw like this. So roughly speaking, it's the stuff which lives within the causal development of whatever is sitting between the boundary region and the minimal surface. That's the entanglement wedge, and that's the part of space-time which knows only about what rho A knows in the CFT. And then it's customary to write rho A as the exponential of minus an operator, which we call the modular Hamiltonian. And then the modular Hamiltonian, what is that in the bulk? And so in some cases, the modular Hamiltonian has a geometric action in the bulk everywhere, but these are very special cases. As a general statement, what we know is that the modular Hamiltonian generates boosts which act in the directions orthogonal to the minimal surface in a neighborhood of the minimal surface. So if I'm close enough to the minimal surface itself, what H mod does is that it generates these boosts. Any questions about what I said so far? So,
Has there also a temperature in this modular Hamiltonian?
But this temperature is just going to set for me some units of this modular Hamiltonian is really dimensionless, or the modular time is dimensionless. So if I wanted to stick in something dimensionful, it would just set for me units of modular time, but it's just a choice of units, so it's not very important. Any other questions or comments? Okay, so I want to make I will push this board down and take this one out. I want to make a list of things that we know about this modular Hamiltonian.
Sorry, modular Hamiltonian is something in the dual field, so why does it generate something in the bulk?
Oh, well, any operator in the CFT should have some representation in the bulk. In the sense that this is a duality. So we write operators in the bulk in terms of boundary operators, and maybe we can do it the other way around too. This is sorry, is that an answer? Is that a satisfactory?
So the boost is really the dual to the...
Yeah, the boost is the dual of the modular Hamiltonian, yes. There is a subtlety there because this boost only, the modular Hamiltonian only really acts as a boost in what's called the closed subspace in the bulk. So there is some set of states, in fact, a very large set of states where it doesn't have that interpretation, but those states wouldn't really be interpreted geometrically anyway. But insofar as I can draw this drawing, it's also okay to draw this arrow in a neighborhood of the minimal circle. Yeah.
Well, if psi is an eigenstate of the CFT, even in that case, the bulk dual of the reduced density matrix of A is a space dimension?
Well, my favorite eigenstate of the global Hamiltonian is the ground state, and then we're talking about pure radius, and nothing I said here changes.
So the bulk dual of rho A is still a space-time. It's the space-time bridge, not the spatial bridge of A.
Oh yeah, definitely. You see that's actually a point that I wanted to raise next. So very, very good.
So I have like one more question about the drawing. So when you drew the boost, like you also went along the boundaries, and like I'm not sure if these are null boundaries, but like it really acts, I think, at the neighborhood of the bifurcation surface of SA, right?
Oh, you mean, are you complaining this arrow is drawn too long? Yeah, that's for the purpose, that's for the benefit of the people behind the camera. On the other side of the screen, yes.
But you agree?
This is no, absolutely, and I think I said it, and if I didn't, then I apologize. But we're supposed to take this arrow seriously in a closed neighborhood of this thing. Actually, it's okay to draw this arrow long because in the Lorentzian context, what we mean by a small neighborhood is that the distance, the invariant distance from the minimal surface to where I draw should be small. But this is a light-like direction, so all of these distances are small. Actually, this arrow is fine. Okay, but yeah, it's in a small neighborhood. Okay, any other points or questions? But it's really great that we're having this Blackboard talk. I'm praising myself here because I would never generate so many questions about this stage of the talk if this was a slide. I would just flash it and keep going. So.
We have, everybody knows that because they don't want to refer to parts.
That's right. Okay. So I want to talk now about the evolution which is generated by H mod. So exactly about this arrow. Let's list some facts about that. So a fact is that it preserves S of A. This is H mod of A. It preserves S of A. That's obvious because any unitary is going to preserve that. So that's not a very interesting statement. Any unitary which acts only on A and not on the full system. But it does more than that because it preserves the whole row of A because it's e to the negative H mod. And so obviously H mod will commute with the exponential of H mod. So in the bulk, this means that this H mod preserves the minimal surface. We have already seen it here because this boost is precisely the boost that vanishes at the minimal surface. The boost for which the minimal surface is a fixed point. But it also preserves all of the entanglement wedge. And so this entire object here, which I will draw for us again, this entire thing is entirely preserved by the action of H mod. So from the viewpoint of someone who only knows about the entanglement wedge in the bulk, or from the point of view of someone who is in the CFT and who only has access to the region A, H mod is a symmetry. Any questions about that statement? I think that's clear. It's a symmetry which, like I said, it preserves the entanglement wedge, but it doesn't mean that it's completely trivial, because if I have my favorite observable, for instance, maybe some correlation function of some operators that are here, as I apply H mod, it's going to get moved over here. That's what that arrow meant. So it does not, it keeps a state invariant, but if I put a particular operator in the, which is part of the operator algebra of A, then that operator will get moved to some other operator. And so I will say that this is an, the fancy word is that this is an automorphism of the operator algebra of A, but I'll just write it here, maps observables in A to themselves. Okay. So if I just have access to the entanglement wedge, or if I just have access to the reduced density matrix, then this map that reshuffles the observables is something that I will not be able to detect. So as far as the physics goes, rho A is unchanged by the evolution of H mod. So this is an unobservable symmetry for me. But it does matter if I have my particular set of labels that are carried by the observables. Yes. And I just hope that you appreciate that the words I just said are exactly the same set of words that we use when we talk about gauge theory. Because there are some gauge invariant quantities that don't depend on gauge. But if I make a gauge transformation, the observables seem to get reshuffled, but the physics stays the same. Or our labeling of the observables gets reshuffled, but the physics stays the same. So I want to say that this is a mark of a gauge symmetry. And what these things are like gauge transformations. Now, one way.
So by this you can then also classify the physical states.
Say what?
So this defines some of the physical states.
This defines the physical. You mean the gauge invariant states?
Yes.
I don't want to say that this is not the way that I want to go. I want to construct a connection and then construct a Wilson loop out of that connection. So I'm not really asking which observables are invariant under this gauge symmetry. In some sense, these are the observables that, which like rho A, which commute with those with the gauge transformation. But this is a state-dependent statement, because if I go to another state, I will have a different H mod and I'll have a different symmetry. So this is not a dynamical statement that's supposed to apply across the whole theory. I'm just saying that for a given state, this is a symmetry that I have, and it's an internal symmetry. So I have some connection to define. But this connection is never going to be a dynamical object for me. Yeah.
I'm a little bit confused because it seems like there's sort of just one operator that generates the symmetry, so it's just a global symmetry.
Yeah, it sounds like it's just U1. So let's talk about that in a moment. Actually, no, this is the right time to talk about it. Yes. So this statement. Oh, okay. So it maps observables. I'm just gonna say one more thing about H mod. It maps these observables to A, and in the bulk, I already said this before, but let me just say it here, acts as a bulk boost. Boosts are orthogonal to the surface. So now to answer Craig's question, yeah, there are actually more symmetries like that, So to make this statement that I'm dealing with a gauge symmetry, I didn't have to have H mod. I could have taken any operator instead of this. Let me call it Qi. And this Qi would have to satisfy the condition that Qi commutes with H mod. Any operator which commutes with the modular Hamiltonian is also going to keep this rho unchanged. And so I will have a much larger group of symmetries. It's not just the H mod, it's anything that commutes with the modular Hamiltonian, that is that generates this gauge orbit. Any other questions about that?
So I think the statement, so there's a state dependence, right? So the statement
Yes.
of gauge symmetry, so this is symmetry of the bulk state that's dual to.
It's clearly I have to move on to the next blackboard to assuage these things, because we're used to thinking of, as soon as I use the word gauge, we like to think about like gauge theories like U1 or SU2. But that's not what I mean. These are dynamical theories. But there are other contexts where we see gauge symmetries appear, and the most famous one of them is the construction of the Berry phase. This is famously an integral of the Berry connection, and there's a gauge bundle there. So I'm actually talking about an analog of that. Notice that that phase is also not dynamical. It's just something we read off from the Hilbert space, and it doesn't reflect a dynamical property of the system. It reflects what we did to the system, how we changed around the Hamiltonian. That's what Berry phase does, and my phases will do a similar thing, not a dynamical thing. Okay, but so I just said anything that commutes with the modular Hamiltonian is going to generate this gauge symmetry. I just have to write one more thing here on the final in this final point, because H mod generated the boost, but these other things that commute with H mod are not going to generate the boost. They will generate something else, but that something else clearly has to also leave the wedge invariant. So these things could be completely non-geometric, because we're not guaranteed that a generic operator from the CFT is going to nicely respect the locality of ADS. But if it acts locally, this Qi, any one of these things, then it has to act locally in a way that preserves this thing. So on the minimal surface, it has to go sideways, because it has to keep the minimal surface invariant. Yes? The edge of the wedge, that's a funny phrase, but the edge of the wedge has to be invariant. So the only thing I can do to the wedge is, to the edge, is move along it. Yes? So these other QIs, if they have a geometric interpretation, they will be diffeomorphisms, which are diffeomorphisms that on the minimal surface act longitudinally. They map the minimal surface to itself. And Michał had a question.
Yeah, so my question is, like, when you write modular Hamiltonians, you really mean like the logarithm of the density matrix, or you mean like the logarithm of the density matrix minus logarithm of the complement?
Oh, that's an excellent question. So I want to be, this is a question that if we talk about it in deep, I just would like to leave this aside for after the talk. This is a very confusing technical issue, which the reason why this paper is promised in March is that we have understood this issue. We have, yes. But it took us a long time. So this would be a very confusing discussion for this topic if I were to talk about it. Okay, so so good. So now I'm going to slowly move to the other side if you need to move the camera. Since I have this gauge, I made a big deal about talking about the gauge symmetry and gauge transformations. So now what I have to do, all of this was so that I would be allowed to draw a bundle, because that's the correct language in differential geometric terms for what I want to talk about. So whenever we have a gauge symmetry, we're really talking in differential geometric terms about a fiber bundle. And so I have to tell you what the base of the bundle will be and what the fiber is going to be. So the base is going to be the different modular Hamiltonians. This will be the base of my bundle. And then the fiber directions are going to be, well, there are various ways to read out what I mean by a fiber bundle here, but it has to be something that transforms under these gauge transformations. So from the CFT point of view, this would be, for instance, a set of labels on the observables in A. I started with some basis of my operator algebra, and then that's the object that I care about, that will be transforming. From the bulk point of view, this is a very natural thing to do, because whenever we describe space-time, we always use some coordinates, yes? And if I draw a set of coordinates, for instance, this is my coordinate and this is my other orthogonal coordinate, that thing is going to change under this modular transformation, under this modular boost, yes? And so, modular transformations, H mod, is going to take a coordinate system in the neighborhood of this minimal surface, and then if I act with this gauge symmetry, it's going to move it in some way. So from the CFT point of view, my gauge direction is spanned by different labels on the operator algebra. From the bulk point of view, it's the set of possible coordinate systems that I could impose in the neighborhood of the minimal surface. Does that make sense? I want to stop using these clanky phrases such as a choice of coordinate system on a minimal surface or a basis choice for an operator algebra. I'm going to call this thing a modular frame. So these things are modular frames. And so the vertical direction here consists of different modular frames. And that's, okay, any questions about that?
So, modular Hamiltonians, you mean all the QIs? Yes?
All the QIs, yes. So the QIs are going to move about these. They are going to, like I said, the QIs that are not H mod are going to maybe move sideways along the minimal surface. H mod itself is going to perform boosts. But generally, these are transformations that act in the neighborhood of the minimal surface, but vanish on it. Yeah. Well, no, alongside it doesn't have to vanish. The boost vanished. Right.
So good. Just maybe more basic. So the base, when you say the base is on all the modular Hamiltonians, so does that correspond to fixing the state but varying the region A, or?
Yeah, that's an excellent question. So the next, that's right. So the next thing that I would have to do here is I have to define a connection on this bundle, and then we'll be computing some holonomies. And then the holonomies will correspond. So let me just talk about that. So what do we do in differential geometry when I have a fiber bundle? What I ask, a typical question that we ask is, if I go from this point in the base, I have this modular Hamiltonian, and move to some other modular Hamiltonian, for instance here, yes, and I started with some particular modular frame, then, I mean, in general, I can go to any modular frame and that sits above my next modular Hamiltonian. But the whole point of a connection is that I am choosing a special one to go to, and this is what we call parallel transport. And so a choice of connection is a choice of where I'm going to land on this fiber if I started here. And then I can go from here, maybe in a, actually let me draw a little rhombus here. So I can go from here to yet another point and do it again, okay? And then I can complete this rhombus or this parallelogram in a different way. So go from here to there, and maybe from here to there. And let's say that I ended in a different place. What do we call this? Well, if these arrows are large, then this is what we call a holonomy of this gauge connection. Or in other words, a Wilson line, or a Wilson loop. But if these arrows are infinitesimal, and that's the reason why I draw a little parallelogram, so I go in one direction, another direction, I do it the same thing, but in the opposite order, then this thing is what's called the curvature 2 form of this connection. So if it's infinitesimal, then this is the curvature 2 form. This is just a review of what we learned in our classes previously. And yeah.
So what you're trying, and like maybe you're getting there, like, are you going to be trying to use like the fact that these modular Hamiltonians are geometrically defined, so that there's a relationship between this abstract.
So we can formulate the transport problem abstractly in the CFT. It will have some answer. But insofar as it has any bulk avatar, this bulk avatar is going to be some transformation in the bulk. So this is the goal is to find an object in the CFT that, for example, matches the curvature in the spacetime. I have a general CFT object, or a general quantum mechanics object, in fact, this connection, and Wilson loops built out of it. Under some circumstances, we'll have a nice interpretation in the bulk.
Are you going to be super generic about kind of regions that you consider, or like you're looking at, for example,
This question is a little too early, but yeah, I will talk about this. So we define this holonomy, and so we get this holonomy if I have a choice of connections. If I define the connection, if I know what it means to go horizontally or parallel in this bundle, then I will have some holonomy. And then Suki's question is, what kind of trajectories will I want to consider? In general, this fiber bundle allows me to do a lot of things because I can just change the modular Hamiltonian at will. So let's think about this problem. I could start with some state, take the region A and take its modular Hamiltonian. I'm just going to change the global state in some way. Maybe I can even change it so that I'm only making changes on one side, but not on the other side. Yes, that would really change the modular Hamiltonian here in terms of its basis, but the other side wouldn't know. So that may be an interesting thing to do. I will not be doing that. Instead, I want to fix the state and I want to vary the region. And the reason why fixing the state and varying the region is interesting. So I vary the region, the modular Hamiltonian changes. So I am doing some trajectory here. Yes. So this falls very well in the purview of this picture. The reason why this is interesting is that I'll just briefly draw another picture. Whoa. Okay. So this picture is not going to stay very much on the on site. So let me draw it on the backward So I have I can start with some region A, okay, and then maybe I will go to some other region, which is this region here. That's going to be my A prime. So I go from this minimal surface to that minimal surface, yes, and then I will go from that one to yet another one, which lives literally higher up. So from here to there, okay, I'm going to call it my A double prime. That's one way in which I can take two steps in this bundle. But another way in which I can take this two bundle is to go not from here to there, but from here to there first, yes, and then from there to there. Does that make sense? I'm just drawing a bulk version of that little rhombus that we have over here. And if the result is that I went from here to there and from here to there, and my coordinate system that I was dragging along ended up the same this way, then we would say that the bulk is flat, because it doesn't matter which way I travel, I arrive at the same. I arrive at the same. With the same internal coordinate system. But in general, that will not happen. It certainly will not happen in ADS. If I take a surface and move it here and move it that way, then it will always end up being transformed. It will end up being transformed by the bulk curvature. Yes, that's what curvature is. So I'm telling you that this bundle here, defined in the CFT, really has the same action, or it was defined to have the same effect as the curvature and as the connection that we use in the bulk for solving bulk transport problems. And so this is why this is a candidate for answering the question, what is ADS curvature from the CFT point of view? So I promise that I will give you an answer, and this is my proposed answer. It also answers Suki's question, what kind of trajectories should I study? It's really important here to fix the global state and just vary the region, because that's what the geometric problem in the bulk is asking me to do. Okay.
Sorry, but in this scenario, if you're fixing the global state and you vary the regions, then the modular Hamiltonian is defined relative to that subregion. So you have changed the modular Hamiltonian as well in a way that is not only geometric.
So I'm changing the modular Hamiltonian. That means that I'm using. I'm
saying that this can't be this track to get a non-trivial connection here is not purely geometric, because you also change the state necessarily in doing this when you change the subregion. So your modular Hamiltonian has changed.
I disagree with the logic of that comment. In fact, I would always. You're making some assumption here that if I change the modular Hamiltonian, then I will not be talking about the same state anymore. That's okay. I'm always talking about the same global state. So there's the same geometry. I'm just changing what I mean by my subregion.
But that changes what you mean by, you change what you mean by a subregion, but that, if I have a local state under the subregion, then you change what you mean by a subregion. That does not also change your local state, even the result state.
Can I follow this? Because I think I understand what you're saying.
To be honest, I have no idea where this question is coming from.
So can I turn to the
Sure.
Clarify, and maybe you're gonna say that I'm not saying the right thing, but suppose that like these three slices, like these three A5 and double prime lie on the same canonical constant time slices on the boundary, right? Then we always talk about the vacuum state in a CFT, right? But then if we are on a cylinder, then like you consider a state that is defined on some wiggly surface, then it's not really like it doesn't really correspond to the canonical vacuum, right? What I say is that you have a
you're taking a very funny state, which is a reduced density matrix drawn from a very ordinary state, which is the ground state.
But you evolve this ground state like in an inhomogeneous way.
Yeah, and what's the problem with that?
Well, I mean, I would say that like we change the state in a way of that is kind of.
I change what I mean by my state versus somebody else's state, but the global state didn't care. And similarly, if I solve a bulk transport problem where I take a minimal surface and I drag it along and arrive someplace, are you saying that there are some surfaces that I shouldn't pass through or something? Let's say I would say that the very problem of understanding bulk curvature requires us to always be changing what I mean by the region. Because I mean, if I never change what I mean by the region, then what am I doing? The region is fixed, and I'm not traveling anywhere. I always have to do some travel in more than one way, arrive at the same point along two different trajectories, and compare. But along the way, I have to be changing the surface. I have to be changing the region.
But as long as you're using those QI operators, so your HMOD is among those QI operators, as long as those are the stabilizers of the state in question, then you're not changing the state by construction, but you are doing something non-trivial in the bulk.
I am changing. No, I am changing. So I am changing
the state.
No, I'm changing the state. Changing the state means going from here.
Changing H. You're not changing the state on which H acts. Precisely. That was precisely your point. That there's a large automorphism group of the state that you're interested in. You're acting with members of this group on your state. So as long as
if I act with members of this group on the state, I'm moving vertically here, then I will never go from one modular Hamiltonian to another. That's the whole point. I need to find that to go. Okay, let me try to say it in yet another way. I need to. Can you say state? You need to go. No, I mean. Okay. Sorry. Preserve the state. That's okay. This would be. Yeah, that's what I mean. Sorry. Yeah. Preserve this state, the density matrix.
The last question on this topic.
Yeah.
No, it's so the modular Hamiltonians for different regions generically live in Hilbert space of different dimensions. Could you tell us a bit how do you do this?
So there is so one answer. This is actually the same question that we have asked. No, but let me just give you some set of partial answers. So one is that there is a paper by Aitor Lewkowicz and Tom Faulkner where they explain in what sense I can think of the derivative of the modular Hamiltonian as an operator within the Hilbert space of that region. So it is apparently well defined and certainly in conformal field theory to do so. And so that's a technical answer to your question. It doesn't clarify anything. I'm just giving you a reference. Another way to answer this question is to say that if I just work with the two-sided problem, I carry one modular Hamiltonian and the other modular Hamiltonian, then I never have to run into any problems because there are always modular Hamiltonians on the global state. That turns out to have an extra subtlety that comes with it, and it's that subtle that I don't want to talk about. But modulo a subtlety that I will not be discussing, you can just study the two-sided problem and then the question just disappears entirely. Okay, so yeah, so maybe I was confusing you with my usage of the word state. I have to go from one region to another region to another region. So I'm always changing row A's, and that's what I mean by changing the state. but I'm drawing all of those rho A's from the same global state which remains unchanged. I'm always traveling through the same unchanging space-time. I mean, unchanging in this, maybe it has time dependence, but it is not a space-time that I'm varying by hand along the way.
Yeah, sorry, we can discuss this after. I just want to check. So with the space of modular Hamiltonians, this is the space of the total, the full modular Hamiltonian.
You mean the ones that are two-sided? Is that the question?
Yeah,
or,
it's the space of two-sided modular Hamiltonians.
yeah, let's say so that.
Then I agree. That's fine.
Okay. Then
Okay, cool. Thank you. Good.
Sure. Okay, good. So, okay. So so what have we done so far? I have explained what bundle I have on mind. Why the parallel transport problems I want to study is interesting. It has something to do with bulk curvatures. It will not exactly compute for me like literally the Riemann tensor at some bulk point because I'm always dragging surfaces and not points. Yes. So what it gives me, what will generally give me, is something that we could call the radon transform of the curvature tensor, because it will always take the tensor, the curvature tensor, but then integrate it along a surface, and that's the object I will get out. So it doesn't explicitly give me the bulk curvature, but it gives me some integral transform of it, and that's already pretty good. Okay, so, and you know what kind of trajectories we will be studying, so I think that we have the first half of the talk is completed. Any further questions or not? I would, yeah.
Just a question about the space of these modular Hamiltonians. Like, if let's say you just rescaled H mod by 0 or close to 0, then it looks like you would get a state that would be very high.
I will not rescale H mod because I want these H mods to be normalized so that this is true and rho is normalized. So I will not be multiplying H mod by any number.
Okay, but the space has to be such that the associated reduced state would always be compatible with the global state.
Yeah, but I already have a global state and I'm just drawing it. So that's the thing. I'm not just considering a completely random set of modular Hamiltonians. I take a particular fixed state because I know it has a bulk representation as ADS, and I want to study that state. So that global state or that bulk spacetime. So I will draw from it a set of modular Hamiltonians and draw them here and study this problem. So it's true that I can take a lot of trajectories here, which would not be sensible trajectories from the bulk point of view. And what would that mean? I don't know if I can come up with a trajectory for which literally no global state exists. Maybe that's possible. I haven't thought about this problem. But if I come up with, but even aside from that issue, if I take some completely crazy trajectory here, it will just not correspond to any well-behaved bulk spacetime. So I will be studying something that is of no interest to me as a holographer.
I have one other. Can you get any dynamics? You're defining a not much stuff, but can you get any dynamics to it? Can you get an Einstein equation?
Yeah, that's an excellent question. That I know that one of my collaborators is really obsessed by that question. But anyway, we don't have an answer. We would like to be able to get. Yeah. Okay. So maybe I'm going to take like 2 or 3 minutes to explain why this curvature, why I had this other title, which is modular variphases. So what does it have to do with modular Hamiltonians? Yes. So not modular. What does it have to do with variphases? So let me remind you what let me not remind you. Let me study a very particular instance of this thing where I'm not taking literally all modular Hamiltonians that are possible, but I'm just going to take a very special family of modular Hamiltonians, which in some basis can be written as E0 and infinity. But what I mean by this row and this column will change. So what are these things? These are modular Hamiltonians that tell me my state is actually not entangled, it's pure. Yes. And but which state is it? Well, it depends on what state I have here. Yes. So if I just study this family of modular Hamiltonians, then this bundle thing is the bundle of what? It's the bundle of ground states of this modular Hamiltonian. It's the bundle of ground states of this object. So let me write here my base with this restriction consists of ground states. And then what are the fibers? The fibers are the transformations which commute with the projection onto that ground state, there's only one thing that I can do that commutes with the ground state that acts non-trivially on that ground state, which is I can attach a phase to it. So these modular frames that I have over here, this is the analog of the boost in the full picture, will be just the ground state itself times a phase.
You're assuming that the ground state's unique?
Yeah, well, I said I'm taking the modular Hamiltonian, which is this. So this is a single row and single column. Yeah, I'm just restricting my problem to a smaller problem. So what we have evidently is a bundle of ground states with phases spanning the fibers. So I hope you can recognize that this is literally the construction of the Berry phase. And if I now take some closed loop here, I will in general generate a holonomy, and that holonomy will be a phase, and that phase is called the Berry phase. So does that explain why I have these two titles there? Any questions about that or any comments? Of course, I have to tell you that so far what I've stated is just stated the problem. I haven't stated the solution. So after I state the solution, which is after I give you a connection here, then we would have to go back here and confirm that this connection is indeed the connection that Berry defined. Actually, we won't have to do that because on this bundle, there exists a unique connection which is compatible with the projective structure of the Hilbert space. So in fact, if I construct any connection, it will always be this one.
So, yeah. Correct, and maybe I understand. So you're saying that we have a modular Hamiltonian, we find its lowest eigenstate, and then as this modular Hamiltonian changes as a function of external parameters, say like the pair of points on the boundary, then when these parameters go back to the origin, then we're gonna pick up some overall phase, and this is what you're gonna call the. I mean, this is the Berry phase, right? And this is what you're gonna have as the second type.
Yeah, yeah, that's right. Okay, good. So I think that's more or less all I wanted in terms of stating the problem. So now I just have to tell you the rules for parallel transport. I've been going without notes, but I think I'll take some notes now to make sure that I don't botch it. So let's imagine, there will be two parts of this board. There will be a CFT part and there will be an ABS part. And I also stress that the ABS part only applies when these QIs have a geometric representation. So we have to go to the code subspace on the ABS side of things. And then we have to take those QIs which act geometrically. So which more or less we have to project the QIs onto the code subspace to draw this second part of the board. So there'll be a CFT part and an ABS part. Let's start with the CFT part. So suppose that I have some family of modular Hamiltonian, I'll call it H of lambda, and suppose that I can write it in this form. So maybe I want the dagger here. Good. Now I'm going to take of course, this U here, which I wrote down here, it's ambiguous up to an action of the modular zero modes, up to a change of frame, because this Q, what I said, the Q's that commute with the modular Hamiltonians, if I put such a Q here, and if I put such a U constructed from the Q here and there, they will just pass through and annihilate each other. So this U is defined up to precisely our gauge ambiguity. So we can think of these fiber direction as being literally the choices of U that work. Okay? Or the choice, not the choices of U that work, the choices of base which preserve the form. Okay, now I will. So good. Then I will just write down what the derivative of U is with respect to lambda, and it's an identity that follows from this form of H, that this thing is equal to this. So there are two terms in this equation which are interesting. Let me start talking about the first one. So this first one here is something that, because I have the same u and d has a dot, that means that it commutes with the Hamiltonian itself. Yes. So this, in fact, is itself a modular zero mode. Yes. Now this guy here is an upper. Oh, okay. It's a modular zero mode. Yeah, that's right. Now this one here is a different beast. It changes it unitarily changes the spectrum of the Hamiltonian. So this one is something that changes the spectrum of the Hamiltonian. This one is something that, because I have a d dot, this is the piece that precisely doesn't change the spectrum of the modular Hamiltonian. I notice that this object here is defined up to addition of zero modes. Because if I add a zero mode to it, it commutes with H by definition, and so the equation remains true. And so the way that we can define a connection, so what do we have to do when we define a connection? We have to find some way of choosing this U dagger U dot in a way which disambiguates this change of the modular of the zero modes. So a condition that we can impose, it's a natural condition to impose, is that I will take this object, and if it has any zero mode component, which it can have, I'm going to project it out and extract from this just the piece that has no zero mode. And that process of extracting out the zero mode proportional piece from this is what we call the definition of a connection, or a definition of parallel transport. See, when I go from my earlier age to the new age, I'm always acting with some object like that, and different choices of that object will land me here, there, and there, and I just have to choose, find some way of disambiguating this. And so, if you like an equation, then I could say that the connection, that's the thing that I have to add to the ordinary derivative to take my arbitrary gauge choice into the parallel transported gauge choice. The connection is going to be minus the projection onto zero modes of this quantity minus U dagger U dot. Yes, there are two minuses, so they will cancel out. So this would be the connection that I define. Now, it may not be totally obvious from this definition that this is the right definition. Yes.
Say projection. This is not orthogonal projection with a
yes. Yes. It may not be totally obvious that this is the correct notion of a connection to define, but we can in fact check this as a consistency condition by checking if it actually is the same as the Berry connection. If you remember, I told you that there's actually a unique U1 connection over the projective Hilbert space. So, so something would have to be wrong if this wasn't that. But luckily it is that. Because let's think about what U is. What U is something that diagonalizes the Hamiltonian. So U consists of row vectors, and U dagger consists of column vectors. Maybe I said it the other way around, which are the eigenvectors of this Hamiltonian. So when I take U dot and U dagger, a component of this that generically I will get will be something like EI overlap DEJ, and this would be the IJ component of the connection. But that's exactly what the Berry connection is. So this is the kind of object that we want. Yes, this is the known formula for the Berry connection. Any questions about that? This set of comments? Okay, so now this is the CFT construction of a connection. Now that I know what parallel transport is, I can go ahead and compute these holonomies in the CFT. That problem is now done. Now for the bulk. So the only way that we have to connect this story to the bulk story is the statement that the modular Hamiltonian generates these boosts, which are orthogonal to the minimal surface, and then we can extend that statement to the other operators which are zero modes, which generate the other directions in the gauge fiber those QIs that I wrote down before. If we take those QIs which have a representation as diffeomorphisms that should take me along the minimal surface, it's diffeomorphisms that map the minimal surface to themselves but have some longitudinal component. So either way, the only way that I can have a bulk representation of this story is if I represent everything in terms of vector fields in the bulk. And so H mod has a natural, there is this generator of the gauge of the boost symmetries. I'm going to call this C mod. Okay. And I have a family of those things for every lambda. I mean, I have a family of it spanned by, parametrized by lambda. And I'm going to write down exactly the same equation that I have over here. So I will take the dot of this H mod, and I will equate this H mod to two things. One of them is going to be the commutator of some new quantity, which I will call eta and H mod. Okay. That's exactly like what I have over here. And then there will be another quantity, which I would have to write down explicitly, which is the piece that is proportional to the zero mode. And so to do that, I'm just going to, without writing it explicitly, one thing I know is that it's the, yes, it's the zero mode component of H dot. So if I define a projector onto the zero mode, onto those vector fields which are zero modes in the bulk, then this thing is literally that projector of psi mod itself. And this is an equation which is just a bulk avatar of this exact CFT equation. And what I have to do is to do the same thing that I did before. I have this eta, which is a vector field which generates, which takes my minimal surface and takes me to another minimal surface. And I have to take the projection of that eta, and minus that projection is going to be my connection gamma. This is the bulk version of what the connection does. Now, all of these were abstract words, so let's talk a little bit about what this means in practice geometrically in the bulk. So I started with some minimal surface, and then I'm taking this minimal surface to some new minimal surface over here. Okay? And I can do it in many ways, because I can write down many vector fields which will take this surface to that surface. But what is the ambiguity? The ambiguity is precisely those vector fields which travel along that, which map this minimal surface to itself. So what I want to do is to find an eta which has absolutely no component in those directions which map the surface to itself. So how would I do this? The first condition is that it has to be orthogonal to the minimal surface so that it doesn't travel alongside. That will kick out this, eliminate this piece of the gauge that was generated by those QIs, the things that take the minimal surface to itself. I also have to eliminate the boost component of this eta. So in general, this eta could take the minimal surface and map it to the other minimal surface, but boost the neighborhood. I also want to eliminate that. So what parallel transport does is maps this surface to the other surface in such a way that it will pick up no boost component along the way, and we never travel horizontally or in parallel to the minimal surface. These are the two geometric conditions that define this object. Okay, any questions about that? So more or less by construction, when I take the holonomy, which is and if you're a purist, then you might ask, what is actually the parallel transport? Once I find this beta, I have to do parallel transport along that eta, which satisfies the conditions I just mentioned. So in the bulk, parallel transport is enacted by the Lie derivative along that eta, the eta that has all the zero modes stripped off from it. Okay, so I have this is all the things that I want to tell you in terms of the the technical stuff, and the only thing that remains is just to tell you about the envisioned application of this. Are there any questions before that about the mechanics? Yeah.
So is there an adiabaticity assumption in this process?
Yeah, the adiabaticity. Yeah, that's right. So the adiabaticity assumption is that you want to. Yeah, so in field theory, this adiabaticity assumption is essentially going to be automatically satisfied because what we want to say is that the change from one system to the other system is not too abrupt, but it's continuous. But if it's continuous, then I will just take small enough steps along the way, and that will be okay. The kind of situation where I could not satisfy the adiabaticity condition would be if I was doing some discrete jumps. And so, for example, we thought about computing this quantity in quantum mechanics for some state in a 3-qubit system. And then the first idea for that was, let me just go take the 2 qubits and the other 2 qubits and the other 2 qubits and form a loop that way. But the discrete transformation of going from this 2-qubit to 2-qubit system is exactly what would fail for this adiabaticity. So a field theory setting doesn't really have an analog of this problem if we're only doing geometric transformations. I think that this is effectively what this paper I mentioned by Aitor and Tom. This is effectively what that paper formalized, the idea that I can slowly enough move from one region to another region, so the operator in the new region, or the difference, can still be thought of as an operator in the first. Yeah.
And a follow-up, so you had a paper in 2017 in December about like doing similar stuff in a sense, and also like we're discovering some structure with connections and phases, but for these OP blocks. I mean, I don't want to follow on this because it might be slightly outside, but these are like a direct relation.
This is enough. So I mentioned, I said these enigmatic words that this thing is a very multi-purpose object. So actually, that is also a special case of this construction. It's a special case where I take a trajectory which takes me not in the prime-like direction, but this direction that we did before. And so in that case, this is going to be the connection is valued in the connection will end up picking up that piece of that zero mode, which is not the boost because we're not doing anything with time. But by going from here to here, we end up having to add a piece of the translation along the way. And so the Wilson loop that we generate is just the translational piece, which ends up being the length of the curve in the interior.
I see. And like, your previous work was about the OP block, but like then there was a connection between OP block and
an OP block is like one of these, is like a projector onto one. It's like this piece. It's like a projector onto one of the eigenspaces of the modular Hamiltonian. Not one eigenspace, the whole 0-0 block of it. But that's the reason why I showed that.
So is it like one of these QIs here?
The QIs are the things that commute to the modular Hamiltonian. I'm saying that the OP blocks formed a representation. So they were something that was gauge dependent. And I'm saying that that's something which was gauge dependent. Like here, it's just that state, and it's gauge dependent because it can pick up a phase. Over there, the role of this ground state was played by the whole OP block.
Okay.
Have to watch a little bit the time.
So I'm going to So I'm still on time, yes. But let me just say. Sure. I'm just going to say a few things about where this is. So I'm just going to say a few words about where this is going. So to me, the big theme of this thing is, I mean, for one thing, I think we have computed bulk curvature as a first computation, maybe as CFT, so I'm pretty happy about that. But the bigger theme here is that entanglement functions in exactly the same way as the bulk connection does. That's really the main meta message here. That just by studying the structure of the entanglement and how it varies as I was changing the region, I was able to extract the connection, not the very connection, but the ordinary connection that we studied in our general relativity classes. And that's because the ordinary connection, let's say the spin connection or the Levi-Civita connection in the bulk is, if you take that point of view, general relativity is a gauge theory. But then I didn't have to talk about gravity. Maybe I could have talked about actual gauge theory. And maybe the actual gauge theories like U1, maybe they're also, that gauge is also constructed from entanglement. I don't have any actual data to back it up, but the philosophy of it seems to be that gauge symmetries as we know them, in this case it was the diffeomorphism symmetry in the bulk, and the connection have all the same, and the entanglement share many of the same features in that I can construct a connection from entanglement. In fact, whenever I have an entangled system which is bipartite, I can think of that entanglement as being a Wilson line from the one side to the other side of the bipartite system. That's kind of the idea behind this philosophy. So this was a more speculative and more long-term thing to say. In terms of the more also exciting but more short-term goals, we would like to. It does suggest that I mentioned this problem earlier, that maybe we can study these entanglement Berry phases in small systems, not just in holography. My motivation was holography, but maybe that's not the only reason to use it. And it sounds like by scanning different bipartitions of a multipartite system, which is what we're doing here, perhaps, just perhaps, I might be able to extract a new measure of multipartite entanglement. So that's something that my friends and I will definitely be looking at in the future. And there is also I mentioned this problem that the bulk connection we get out, the bulk computation we get is not a pointwise computation of the Riemann tensor, but always some integrated version of it. So there is a technical question: how do I extract the pointwise thing? Because and maybe this is just technicalities, or maybe there is something actually interesting there. Because a point in the bulk can be defined as the set of all bipartitions that pass through it. So there might be some interesting geometrical structure associated with that. That we're not taking just a trajectory in the space of bipartitions. We're maybe we have to be taking a trajectory in the space of collections of bipartitions, which is what the point is. So maybe that will turn out interesting in the future. And yeah, there are for the more holographically minded people in the audience, it's an interesting question to study what happens when I have a minimal surface, when I have an extremal surface, which does not compute the entanglement entropy of anything. Because then I also have a modular boost, which acts orthogonally. I also have these diffeomorphisms, but they're not related to modular symmetries of any density matrix. So somehow the bulk unifies this object with something else. What is that something else? As in, what is the generator of orthogonal boosts to a surface which is extremal but happens not to satisfy for instance what is it called, the homotopy condition. So we may want to think about that. These are some of the problems that I certainly will be thinking about in the future, and I encourage you to do the same. Thank you.
Exciting talk. I think we should force all following talks to that, to be on the blackboard. That's too late.
I still regret it.
Yeah, I regret many things.
Can you give an example where you take a modular Hamiltonian of a CFT and get a constant negative curvature?
We take so like I said, I am only computing this surface by surface. But when you take a trajectory which I was trying to draw on one of these boards before, so basically take one minimal surface and take it along two different ways from there to some other minimal surface, then you will literally come up with a boost which is picked up by the amount of curvature that's sitting inside that thing. So yeah, that's you can get that.
Okay, so you can take, like, I don't know, some theory with a gravity dual. Let's pick some CFT in 2 dimensions, maybe with a gravity dual. And, I mean, is there an example where you can actually write down what the the modular Hamiltonian is? Can you just plug it into this formalism and get a number? Or
we only know the modular Hamiltonians explicitly in very few cases.
Yeah.
So I forgot to mention this as one of the future questions. So I've always had in mind, I'm going away from your question, but I'll get back to it. But I just don't want to forget it. So I've always been thinking about taking a single connected region and moving it around. But it's interesting to study what happens if I take a two-sided region, because then the modular Hamiltonian is necessarily non-local, or I guess that's the correct statement.
You mean two intervals?
Two intervals, yes. And so we know one theory where we can compute it explicitly. So then it would be super exciting if I could generate a which is this free fermion theory. It would be really exciting if I could generate a holonomy which takes a two-interval modular Hamiltonian, moves around the two intervals, comes back to itself, but the two algebras on the two sides of the intervals exchanged. That would be really nice, yes. Like if I could generate a holonomy that actually swaps the intervals. There's nothing that forbids it from this formalism. So maybe we could do it. For Johanna's question, so there are very few cases where we know the modular Hamiltonian explicitly. So it's hard to convert it into an explicit computation of anything. But it might be possible to write down like the Einstein-Hilbert action in the language of this. So then I would have to retract my earlier statements. This is all non-dynamical. Maybe then it would be dynamical. Lambros is very excited about this way of thinking. I don't know if that's that promising personally yet, but maybe he's right.
One question still. Okay. And I think I give it to you because you had
So your
considerations, I know that.
So your considerations on the PTO side, the CFT side are completely general. So in principle, one could apply it for irrespective if there is a classical gravity dual or not. So can you somehow distinguish, like on the level of those?
Yeah, that's an excellent. Oh yeah, I forgot to say this. That's another thing that I think is an exciting potential application of this. It seems like we can view this as a condition for when a state can have a holographic dual, in the sense that if I compute a Wilson loop, and then it comes out to be something that is completely non-geometric and can't be interpreted as a diffeomorphism going this way and that way, then you would say, oh, like let's say that you had some spacetime in mind. You're thinking probably this is the spacetime that describes it, anything at all. Then you compute this holonomy, and then you end up with something which is completely non-geometric on the CFT side. Then you would say my candidate spacetime couldn't be that because it should generate a diffeomorphism in my geometry, and it didn't. It generated a mess. So we might be able to treat this as a criterion for which states are holographic or not.
I think with this we stop for this session. I think we should reconvene 11:15, right? And let's thank Bartek again.
Thank you. Thank you very much.